Yes. You guys are all making it harder than it is. That's what I'm looking for. You just cross multiply. Now that is multiplying by 5, right? But I'm going to do it at the same time. So when you are solving a proportion, you are just going to do this thing called cross multiplication. All right, so to cross multiply, you're going to make like a cross, like an X, right? And the things that touch along that X are going to get multiplied. It doesn't matter which cross you multiply first, okay? So X times 9 is 9X. Sometimes I'll find kids when they cross multiply, they'll make this another fraction. The point of cross multiplication is to get rid of the fraction. So I'm not going to make a fraction line. I'm just going to multiply the other numbers and write that next to it. So 12 times 5 is 60. Instead of equal to each other. All right? And then if I want to solve for x, I'm going to divide by 9. All right? And 60 divided by 9 is not something that works out nicely. So I'm going to do it in my calculator. If it's a repeating decimal, you can't write it like that. So you're going to use a lot of the simplifying the math button in the calculator here. And so I'm going to math, enter, enter, and that's 20 over 3. You're right behind. All right, so my answer to this one is 20/3. Just know that in this unit, we're going to do a lot of fractions. All right, so you're going to have to get comfortable with that math enter, enter button on the calculator, okay? So this unit is probability. This first section, we're going to work with this thing called experimental and theoretical probability. This is a full lesson, but for us, this is 2 days, okay? Because in a normal year, this falls on a full day, but because of the keystones, that's why it looks like a lot. We're not doing all of this today. We're going to do this over the next 2 classes, all right? So today we're just going to focus on experimental and theoretical probability. So you'll have a new toolkit. This is the last one. So today we're going to work on section 13-1, experimental versus theoretical probability. This is the very first few examples in your toolkit. And the box at the very top of your page is experimental probability. Experimental probability measures the actual outcome and event observed through experiments or data collection. So you are going to be given data that someone did something to get, okay? So it's an experiment. It's not what you'll learn later, theoretical, something that could happen. It's something that did happen. Someone did something to get these numbers, okay? So in this first example, it says Sarah tossed a coin 60 times. She physically did this experiment. She took a coin and she tossed it 60 times. These are her results. It's an experiment because she physically had to do something to get these numbers, okay? I'm on here in 13. So Sarah tossed a coin 60 times. She got heads 35 times and tails 25 times. What is the experimental probability that Sarah will get a tails on her next flip? So when you are writing a probability, it is part to whole. So what I want to do is, to get her probability, we write this as P. So P stands for probability of tails. Right, so this is, instead of writing the probability that she gets a tails, this is called the symbolic form of that. So probability that she gets tails is, on the top it's going to be the number of times she got tails. And on the bottom, it's the total number of experiments. Your denominator should always be bigger in this probability unit, okay? So as I read through this experiment, I see that she got tails 25 times. That's what I mean by number of tails. Out of the total number of experiments, she tossed the coin 60 times. 35 plus 25 is a total of 60. So my probability is 25 over 60. Now I always want to check to see if that can simplify. So 25 divided by 60, math, enter, enter. I want to use 5/12 rather than 25 over 60. So the probability of getting tails from her experiment is 5/12. That's not the actual probability of getting tails, right? If I were to put a coin on your desk right now and ask you to flip it, what are the chances that you get tails? 50-50, right? This is her experiment. From her data, from her experiment, the probability is actually 5/12. She got it a little less than half. Does that make sense? Anybody have questions on the first one? All right, the second one says, now we're going to make predictions. Using the experiment above, if you toss the coin 100 times, what would you expect to get tails? Now, in general, if you toss the coin 100 times, how many times would you expect to get tails? 50, right? 50 out of 100. But I want to use her experiment. So I'm taking away like prior knowledge that it's a 50-50 chance, and I'm using her data. How many times does she get tails? 25 out of 60. We reduce that to 5 out of 12. So I'm going to take her experiment, 5 out of 12, and I'm going to set a proportion with this new number of experiments. So before, she did 60 experiments, and the 60 was in the bottom. Now I'm saying, well, what's going to happen if she does 100 experiments? So that 100 is going to be in the bottom. 100 is the total coin tosses. I want to figure out what this number is. Hypothetically, it's 50 out of 100, but I want to use her data, so I'm going to use the 5/12, and I'm going to put this as an X. And now it looks kind of like the warm-up. It's a proportion, right? I want to figure out what her fraction is going to give me out of 100. And we solve a proportion by cross-multiplying. So I'm going to make this X, and the things that touch along the X are going to get multiplied. So it's 5 times 100 and 12 times X. When you multiply, when you cross multiply, they just get set equal to each other. It doesn't make a new fraction. All right, and then I'm going to divide this by 12 to get that X alone. Now, let's think about what that means. Right, we got that. That's not the answer because I'm looking to see how many times I would get a tails. I'm looking to make a prediction. I can't get a tails 41.67 times. That doesn't make any sense, right? So what you're going to answer is you can argue either one, and I'm not here for the argument. Pick one. Round it down or round it up. I don't care, as long as you know it's somewhere in there, right? So technically that rounds up because of the 6, but then you're going over, and you know, like in the game, the Price is Right, can't go over, so then people say that you can't go over and you got to keep it at 41. I don't care which one you do. Whichever logically makes more sense to you, pick that one, okay? We're going to round it though, because we're not going to say she's going to get it a decimal of times, right? It only makes sense for her to get a whole number here, so we're going to round it. You okay with that one? All right, let's look at the next one. A quality control inspector samples 500 LCD monitors and finds that 450 of them are working. What is the experimental probability that the next LCD monitor chosen is defective? Okay, this person's job is to go through these things and check them. They are physically doing the labor. Anytime someone is actually doing something to get this data, it's called an experiment. This is an experiment, okay? This person did this 500 times. That's the total. What I'm looking for is to find the probability of defective. Do you guys know what the word defective means? And I'm not being a jerk. I'm just making sure. What does it mean? It doesn't work. So what I know is that 450 of them do work. out of a total of 500. So if 450 out of 500 work, how many don't? $50 of them don't work. Does that make sense? If 450 work, then that means 50 don't. So the probability that it's defective is the number of defective monitors, 50, out of the total number of monitors, 500. And then I'm just going to simplify this fraction because I should always check to see if it simplifies. So 50 divided by 500, your calculator has this math, enter, enter. 1/10. 1 out of every 10 is broken. All right, and then it says making predictions. Using the experiment above, using their data. If the company manufactures 15,240 monitors in a month, how many are likely to be defective? So I'm going to take the number that are defective, 1 out of every 10. And I'm going to create a proportion with this new total. 15,240 monitors is all of them. It's a total. So I want to put it in the bottom. The totals always go to the bottom. And I'll call the top X because that's what I don't know. And now it's a proportion. And to solve a proportion, you cross multiply. So I'm going to do this. So 1 times 15,240 and 10 times X. This one works out nicely. So we get, I don't have to round here. I'm going to label it monitors. Since we are referring to something, right, it's how many are likely to have a defect? 1,524 are likely to have a defect. All of the information that we just used is called experimental probability because you are given data from someone who actually did something to get that data. That is an experiment. Tomorrow we'll learn about theoretical probability. We're not going to use data, we're going to use like hypotheticals, okay? So we're going to do some practice on this with our last few minutes. So I'm going to give you your new workbook. You're going to do page 3, numbers 1 and 2. You could draw out the workbook, yes. Okay, so now that we all just about have a workbook, I'm going to say 5 or 6 minutes here so that we can get the answers posted before you leave at 11:03. All right, so it's only 3 questions. So I think 5 minutes is fair with that. So you're going page 3, numbers 1 through 2. The examples are posted on the board if you're not sure if you're looking at the right thing. We've got a baseball player hitting and a medical study. So check those out, give them a shot. 5 minutes, we'll go over the answer. Wait, nope, just those. 1 and 2. Wait. Problems are posted on the board if you're not sure what problems you're looking at. What is this 3 in the corner? You said 3. But this is 4. We're using like a little number. See that one? Sometimes when it copies the old page numbers and the new ones. So the picture, I have a picture of it so you know which one you're doing. It looks like these 2 problems. Make sure to check if your fractions simplify. much here, it's only 3 problems. We're doing them all. All right, so a player got 19 out of his last 64 times at bat. He got a hit. So what's his probability? So you would write this as something like that, like probability that they get a hit. What is that in fraction form? Did anybody check to see if that simplifies? I don't think it does, right? So it's just 19 over 64. All right, what if we go 200 times at bat? Well, we're going to do 19 out of 64 is equal to something out of 200 bats, right? This is 64 at bats total. This is 200 at bats total. We're going to cross multiply. What do we get?
It's like
59 point what? 59.375. So I'm okay with you saying 59 or 60 hits. Round either way, as long as you're in the ballpark. We okay with that one? I'm not showing the work for the cross multiplication there. I skipped that step. But I would cross multiply. 200 times 19 equals 64x. Divide both sides by 64. All right, a medical study tests a new cough medicine on 4,250 people total, right? It is effective on 3,982 people. What's the probability it's effective? So we would write like probability of effective. And it's like, who's it effective on? 3,982 out of the total 4,250. Did anybody reduce that fraction? Nate, what'd you get?
1,991 divided by 2,125.
Thank you. All right. So that's part 1, simplifying the fraction. Question 2 said, well, what if there's 9,000 people? What about them? So I'm going to take my answer from part 1, preferably the one we simplified because the numbers are smaller. And I'm going to set that equal to a total of 9,000 people. And now I have a proportion. So I'm looking to cross multiply here and solve. What do we got? Someone give me an answer here.
8,400.
What is it?
8,400.
30 what?
2.
2. All right, so I'm doing 9,000 times 1991. That's that big number. And then I'm going to divide that by 2125. You get this decimal. So you can say 8,432, or if you want to round that up, 8,433. Either way, that's the number of people. I should label that. I just don't have room. Experimental probability, all of that data was done. That batter physically had to hit 60 times for him to get that data. This person had to test those people who physically had to take the medicine. Okay, so that's all experimental because someone's doing it to get the data. Tomorrow we'll do theoretical. I have no homework for you tonight. The next slide is like the lesson continued. So I'm just going to leave it there. All right?
Would you mind if I solve it like that? What was unexpected work for this?
Sure. Yeah. You should still get the same answer, right?